All right, the last thing we're going to go over in chapter 2 is chemical equations. We've already kind of been using these, but we're gonna delve a bit more deeply into them. So, what a chemical equation is, it's a way that we describe the process of a chemical reaction using those molecular and ionic formulas that we learned about in the previous video. So, for example, if we're looking at the combustion of propane, the burning of propane, this is the gas that you use, to cook your steaks outside on a grill. It's gonna look like this molecule here, which has a common name, propane, and there's only one of these, so we don't stick a one out here. That's going to react with 5 molecules of oxygen gas, and it's going to produce 3 molecules of carbon dioxide and 4 molecules of water. The reactants of the reaction, those are going to be the chemicals at the beginning of the reaction. So those are going to be the things on this side of the reaction. These are the chemicals that you start with. They are going to be listed on the left-hand side of this arrow. This arrow means some change happens. The products, that's what's produced. So that's the stuff that you get at the end of the reaction. So that's going to be on the right-hand side of the arrow. These are the chemicals present after the reaction has occurred. And like I said, these are on the right-hand side of the arrow. You'll notice that the physical state of the reactants are listed. So here we've got gaseous propane, we've got gaseous oxygen reacting to form gaseous carbon dioxide and liquid water. And, it probably makes sense that we're going to write an S in parentheses if it's a solid we're dealing with, G in parentheses, a lowercase g if it's a gas, and a lowercase l if it's a liquid. You may not be familiar with this particular symbol. If we stick an AQ in parentheses after, the compound of interest or the element of interest, what that's telling us is that the compound or element has been dissolved in water. So this is short for aqueous, and that means that the substance has been dissolved in water. Now there's a pretty big deal that comes with writing chemical equations. And that big deal is what we call the law of conservation of matter. And really, when people discovered this law is when chemistry took off. So what does it basically say? It says, look, the amount of matter we have in the universe is never going to change. This is just because this is what we observe. So that what that tells us is that if we have a gazillion and 1 grams of matter in the universe today, we will have a gazillion and 1 grams in the universe tomorrow. Applied to chemical reactions, what it means is in chemical reactions, the atoms that you have at the start of the reaction have to be the same as the number of atoms that you have at the end of the reaction. I want to get a little more specific here. I want to get a bit more specific. If we go back to this reaction, what the law of conservation of matter tells us is the number of carbon atoms that we start with has to equal the number of carbon atoms after the change has occurred. And you can see that happens here, right? We start with 3 atoms of carbon in propane, and we end up with 3 molecules of CO2, and in each molecule of CO2, there's going to be 3 carbon atoms. And that's got to be true for every single atom in the chemical equation. The number of each specific type of atom has to be the same at the start of the reaction as well as after the reaction has been completed. And because of this, we're going to have to do what's called balancing chemical equations. If you ever balanced chemical equations before, then you're basically making sure the law of conservation of matter is working in effect. You can't have atoms popping in and out of existence. We don't let the tooth fairy in science. So we're gonna do what we call balance these chemical equations, and we're gonna show you a method for doing so. It's not the only method, but it's a way that helps you keep track. So let's do this one first. I'm gonna write this reaction up here at the top. So I've got solid magnesium plus silicon dioxide goes to magnesium silicide and magnesium oxide. And you'll notice I've dropped the states because in terms of the law of conservation of matter, that's not going to matter. No pun intended. Okay, so I'm going to draw a line like this, and then I'm going to keep track of each atom. So I got to keep track of magnesium atoms. I got to keep track of my silicon atoms and my oxygen atoms, and the number of each of these three atoms had better be the same on both sides of this line, and this line is representing, the difference in the number of atoms in the reactants and the number of atoms in the product. So let's just assign, given our equation, how many of each type of atom is on each side as the equation's written right now. Over here, there's one magnesium atom. There's one silicon atom. And notice there's two oxygen atoms. So I'm going to make 2 marks for the oxygen. And on this side, it looks like I have 2 magnesium atoms. I have a silicon atom. Oh, I have a third magnesium. See it over here? I better pop that one here. And I have a single oxygen. So there's a couple places I have a mismatch here, right? The magnesiums don't balance. The silicons don't balance. And the oxygens don't balance. Well, I don't know where to start. I want to go ahead and I think I'm going to start over here, and I'm going to say let's add another magnesium oxide. So notice when you go adding reactants or products, you have to add the compound, right? I can't just go like this, add another oxygen atom. Well, I can't add another oxygen atom like this to try to balance it. Why can't I do that? Because that's not what happens. You don't get free oxygen atoms in this particular reaction. But I can add magnesium oxide because that is a particular compound that's produced. So now let me recalculate what everything is. Notice now I have 1, 2, 3, 4 magnesium atoms on the product side. And it looks like I have 2 oxygen atoms over here. Well, I hope you can see now this is a pretty easy fix, right? I mean, my silicons are balanced. My oxygens are balanced. And I need 4 magnesiums, and I can add single magnesiums, right? I can add 4 of these. Well, I'll add 3 to get me to 4. There we go. Everything's balanced. And the way we would write, therefore, this chemical reaction is I'd write a 4 out in front of the magnesium because I have 1, 2, 3, 4 of them. We don't write 1 in front of this because if I write the compound, the 1 is understood. It looks like I didn't do anything to this, so I leave this alone, and then I have 2 magnesium oxides. So the overall balanced chemical equation would be 4 magnesiums react with silicon dioxide to produce I almost got caught there. This is ionic. This would be magnesium silicide, and this would be 2 magnesium oxides. All right, let's do another one. We're going to do just a couple here, and let's see what this one is. Second problem. Looks like magnesium silicide reacts with HCl, hydrogen monochloride, to form silicon tetrahydride and magnesium chloride. All right, let me write this here, and then we'll try to balance it. So I've got magnesium silicide reacting with hydrochloric acid or hydrogen monochloride, and we're getting silicon tetrahydride, and we're also getting magnesium chloride. All right, this is what I got to balance. I'm going to leave some room for scratch work. I'm going to keep track of my magnesiums on each side. I'm going to keep track of my silicons on each side. I'm going to keep track of my hydrogens on each side. And I'm going to keep track of my chlorines on each side. Let's see where we're starting here. Looks like I got 2 magnesiums. I've got a silicon. I've got a hydrogen. And I've got a chlorine. Over here, looks like I got a silicon. I have 4 hydrogens. 4 hydrogens. I got a magnesium. And I have 2 chlorines. All right, what am I going to do here? Well, I'm going to start with the hydrogens. All right, you can see a mismatch here. I need some hydrogens, right? So let's add. This is the only way I can get hydrogens over here is to add this. So I'm gonna just add 3 more to get a total of 4. Yeah? So I changed this side, so I got to change these, and now I have 4 hydrogens, and I have a total of 4 chlorines. So these are balanced, but I messed these up, didn't I? So to fix that, the only thing I can add over here to add chlorines is magnesium chloride. So I'm gonna add one like this. And since I changed what's going on over here, let's see, I now have 4 chlorines and I have 2 magnesiums. Hey, it looks like it worked. It looks like everything's done because I've got 2 magnesiums on each side. I got 2 silicons. I have 4 hydrogens and 4 chlorines. So this is a balanced chemical equation. And I will write 1, 2, 3, 4 in front of the HCl's. And I will write a 2 in front of the magnesium chlorides. And this is a balanced chemical equation. I'll leave this one for you to try on your own. So this one here to try on your own. If you're having trouble with that, talk to your TA, send me an email or whatever, if you're having trouble with this. Let's move on to this slide here. Let's balance some of these. Well, this one I'm going to leave for you because this one, the answer is already given to you. This was the first example we did. So I'm going to leave this one for you on your own. We'll do these next 2, okay? So I'm going to do this one. This is the combustion of methane. So let's see. I'm going to go CH4 and O2. And that's going to give me carbon dioxide. And it's going to give me some water. So that's the equation I have to balance. I'm going to give myself some room to work. And let's see, I've got to keep track of my carbons on each side. Looks like I got to keep track of hydrogens on each side. And I've got to keep track of oxygens on each side. Let's see where we're at. By the way, these reactions where you take carbon-containing compounds and you react them with oxygen, presumably from the air, to get carbon dioxide and water, these are called combustion reactions. They're obviously very important reactions to us because we get a lot of energy from burning. That's what's going on here. These compounds are being burned, excuse me. We get a lot of energy from the burning of compounds that contain carbon, fossil fuels. And that's a great benefit to society, but any energy source that we use is going to have some side effects. And the side effect, of course, of combustion reactions is the release of carbon dioxide into the atmosphere, which has a warming effect. And unfortunately, the amount of combustion reactions that we're running to keep society functioning has put enough carbon dioxide in our atmosphere that we can tell we're changing the temperature of our world, and that's having an enormous number of effects. But that's just something you ought to know. Something you ought to know that's going on. Anyway, let's look here at this reaction. Let's try to balance it. Looks like I got 1 carbon on this side. Looks like I got 4 hydrogens on this side and 2 oxygens. And looks like I got 1 carbon, 2 hydrogens, and careful here, 1, 2, 3 oxygens. Now, when balancing combustion reactions, which this is one, it is indeed a combustion reaction, you want to try to balance the oxygens last. That's a trick that works really well. So if I'm trying to balance my oxygens last, I notice my carbons are good. Let's go to my hydrogens. There's a mismatch. So what do you think we're going to add on this side? Well, the only way I can get more hydrogens is to add another water. And if I do that, I notice I have a total of 4 hydrogens over here and 1, 2, 3, 4 oxygens. Well, I've got my carbons balanced. I got my hydrogens balanced. Now it's time to move on to the oxygens. I just need 2 more oxygens, and that's really nice because if I just add an O2 here, we get to 4. So I would write the balanced combustion reaction for methane. That's what this compound is called. There'd be 2 oxygens and 2 waters produced, and this would be the way we write our balanced chemical equation for the combustion of methane. Last one. We're going to do the combustion of butane. This is a compound that's used in lighters. So let's look at this. Combustion of butane. I have to write this up here because, all right, let's see here. We've got to go C4H8 plus O2 is going to go to CO2 and H2O. That's what we got to balance. All right. Leave myself some room to work. Keep an accounting of my atoms here. I got to keep track of carbon, hydrogen, and oxygen. It's usually what we got to keep track of in combustion reactions. All right, let's do an accounting here. 4 carbons over here. Whoa, a total of 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. And 2 oxygens. What do we got over here? I got 1 carbon. I have 2 hydrogens. And I have 1, 2, 3 oxygens. Everything's a mess. Boy, look at this. All right, well, what can I do? I'm going to try to balance my carbons first. I have 4 carbons over here. Well, the only place I'm getting carbon out is in CO2. So if I got 4 carbons over here, I'm going to need 4 molecules of CO2, right? So let's pop them in here. So I add 3 to get a total of 4. 1, 2, 3, 4 carbons. I'd also messed up my oxygen, so let's count how many of those I have. 2, 4, 6, 8, 9. Let me make sure that's right. 2, 4, 6, 8, 9. Yep, that's right. And let's see, my hydrogens are still good. Okay. There's a mismatch here, right? I got 8 hydrogens over here. I only got 2 over here. I'm going to need a bunch of water. That's the only place I can get water. Excuse me, that's the only place I can get hydrogen out. I need 8 of them. So if I add 3 more water molecules, well, let's see. 2, 4, 6, 8, and 8. That balances. So now I have 8 hydrogens, but I messed my oxygens up, of course. So notice I got 2, 4, 6, 8, 9, 10, 11, 12 oxygens. Hey, I think I got everything balanced but my oxygens right now. I got 4 carbons and 4 carbons. I've got 8 hydrogens and 8 hydrogens, and the oxygens are a mess. But it's easy fix now, right? Because I've got an even number of oxygens over here. I've got 12. And I think you can see I'm going to need 6 of these, right? If I got 6 O2, that gives me 12 oxygen. So I'm just going to go ahead and write the 6 here, like that. 1, 2, 3, 4 carbon dioxides. 1, 2, 3, 4 waters. And my balanced chemical equation for the combustion of butane is going to be like this. C4H8, one of those. The one is understood. 6 oxygen gas gives me 4 carbon dioxide and 4 waters.